In this video, we will review ILM 150104G, Limits and Fits, Objectives 1, 2, and 3. Objective 1, Limits and Fits. Objective 2, Limits and Fits on Prints. Objective 3, Calculating Allowances. Almost all mechanical products you use are assemblies, which means they consist of more than one component. For assemblies to work properly in all of their design environments, consideration must be given to the degree of tightness or looseness of their mating parts. These considerations are called limits and prints. As your machining skills improve, you are called upon to machine complex parts requiring great accuracy. Limits and fits often demand this degree of accuracy. So it is important that you understand the terminology and purpose of limits and fits and can calculate tolerances and allowances if needed. When you've completed this module, you will be able to describe limits and fits used in machining. So our objectives are going to be describe the terminology, interpret them on prints, and calculate allowances. Objective 1, describe the terminology and purpose of limits and fits. Limits and fits is the name and design of mating parts that specifies their degree of tightness or looseness when assembled. The correct application of limits and fits is crucial to ensure that assemblies operate properly in all conditions. You are required to machine parts to a specific size outlined on a print. To do this effectively, you must understand some of the basic terms that pertain to tolerancing and to limits and fits. Nominal size. Nominal size is the size by which you refer to materials and commonly used items. When you order things like bars, stock, piping, and fasteners, you order the item's nominal size. However, if you measured the item, it would likely not be that exact size. For example, if you ordered a piece of 1-inch diameter cold, rolled, mild steel bar, you would likely find that the diameter actually measures 1.005 inches. Pipe fittings also offer a good example of a nominal size not being the actual size. For example, the nominal size of a standard pipe fitting is 3/4 of an inch, but the outside diameter of the thread actually measures 1.050 inches. The nominal size of this pipe refers to its approximate inside diameter. So nominal size is how you refer to the item, like a 2x4. A 2x4 isn't a 2x4 if you measured it. Basic size. The basic size is the size of the feature before you apply any tolerance or variation. For example, the basic size for a dimension of 1.000 inches plus or minus 0.005 inches is 1.000 inches. Likewise, the basic size for a dimension of 30.0 millimeters plus or minus 1.0 millimeters is 30 millimeters. Tolerance. No matter how good a machinist you are, you can never machine a part exactly to size. This is why the draftsperson or engineer allows you to make the part slightly larger or smaller than the basic size. The total amount of this permitted variation is called the tolerance. We'll see some examples of tolerance in Figure 1. Note, as the given tolerance gets more stringent, it typically takes more time and more care to achieve. This makes the part much more expensive to produce. Sometimes the basic size is used as one of the limits of size. It could be either the upper limit or the lower limit. Figure 1A shows the basic size as the lower limit of size. This kind of tolerance, where the variation is in one direction only, is called a unilateral tolerance. When the variation in size can be both larger and smaller than the basic size, the tolerance is called a bilateral tolerance. If the variation of a bilateral tolerance is equally divided on each side of the basic size, this is called an equal bilateral tolerance. Figure 1c is a special case of an equal bilateral tolerance, which is indicated by the symbol plus or minus. If the variation of bilateral tolerance is not equal, it is called it is called an unequal bilateral tolerance. So let's look at these figures in figure 1. Okay, so figure A. This is a basic size callout. Figure B. We have a unilateral tolerance, plus 0.005 inches minus 0. It's unilateral, it's only in one direction. So this one can be bigger by 0.005 inches. The other part of figure B is also a unilateral tolerance because it's plus 0 minus 0.008 inches. So it can only be smaller. So only in one direction. That's a unilateral tolerance. Okay, so then we have a bilateral tolerance. Under bilateral tolerances, we have equal bilateral tolerances and unequal bilateral tolerances. So a bilateral tolerance is in two directions. So this one can be plus 0.005 inches, or it can be minus 0.005 inches. And D is an unequal bilateral tolerance. So it can be bigger by 0.005 inches or smaller by 0.002 inches. If we look at our tolerance ranges, or our permissible variation, our total is 0.007 inches. Our total in our bilateral is 0.010 inches. Our total in our unilateral, 0.008 inches. Our other total in our unilateral is 0.005 inches. And here, again, this was just our basic size callout, which in this case is actually the same as the equal bilateral tolerance. Okay, so those were our tolerances. Now the term limits of size. Although a tolerance can be specified as a permissible variation from a basic size, as we saw in figure 1, it can also be expressed by actually showing the largest and smallest allowable sizes. These sizes are called limits of size, and we'll see this in figure 2. A benefit of being given the limits of size on the print is that as a machinist, you don't have to calculate the specific limits of size for the parts feature. You can simply use the sizes provided. So when we look at figure number 2, if we look at this shaft and hole dimensioned using the tolerance method, so we have 1 plus or minus 0.005 and 45 plus or minus 1. If we look at that same figure dimensioned using limits of size, we can see it's called out as 1.010 to 0.995. This one's called out as 46 to 44. So it's already given for us. The next term we're going to discuss is allowance. Allowance is the intentional difference in size of mating parts at their maximum material condition, MMC. That's another important term. MMC is the largest allowable male feature. In this case, they're talking about a shaft, and the smallest female feature, a hole. So that's maximum material size. So the largest diameter for a shaft and the smallest diameter for a hole. The allowance is always calculated when the mating parts are at maximum material condition. Mating components at MMC are at their worst condition for assembly. So the shaft is the largest diameter, the hole is the smallest diameter. They're at their most difficult to assemble. However, for machinists, starting out at MMC is the best condition because you can remove more material from parts, not yet at MMC, to bring them within tolerance. You must know how to calculate the MMC of both mating parts to calculate the allowance. To calculate the allowance, you subtract the largest allowable shaft from the smallest allowable hole. So in this case, the largest allowable shaft. So we have 1.500 plus or minus 0.005. So the largest allowable shaft would be 1.505. The smallest allowable hole, we have 1.500 plus or minus 0.005. So the smallest allowable hole is 1.495. So these are our two dimensions at maximum material condition. Our allowance ends up being negative 0.010 at maximum material condition. A positive value for the allowance indicates a clearance fit, while a negative value indicates an interference fit. So in this case, at their maximum material conditions, we're going to have an interference fit of 0.010. Let's look at another one. So fits. There are three types of fits. We have a clearance fit, an interference fit, and a transition fit. So a clearance fit, in a clearance fit, the shaft is always smaller than the hole. You can assemble the shaft into the mating hole easily. So in this case, I'm going to get you to ignore this section at the bottom with the 1.001 and 0.995 for now. We'll touch on that in a minute. Okay, so let's look at this hole size first. So the smallest this hole can be is 1.010 minus 0.004. So the smallest the hole can be is 1.006. The largest the shaft can be is 1.000 plus or minus plus 0.005. So the largest the shaft can be is 1.005. So that shaft is always going to be smaller than the smallest hole. So we have a clearance fit. Let's look at them in their other conditions. So the largest hole would be 1.010 plus 0.001. So the largest hole is going to be 1.0, and this should be 1.011. The smallest the shaft can be, we already figured out the largest, now we're going to figure out the smallest, would be 1.000 minus 0.005. So the smallest the shaft could be is 0.995, and when you do the proper math on this, it ends up being 0.016, a clearance fit as well. So the hole is always larger than the shaft, so the parts always fit together. The clearance ranges from 0.001, as we saw in the calculation on the top, to 0.016, the calculation on the bottom. And our second type, interference fit. In an interference fit, the male part is always larger than the female part. You can't assemble them easily. So for example, you may have to use a press to force the shaft into the hole, or use heat or cold to temporarily change the size of the components. So let's take a look at the math on these two parts for an interference fit. Okay, so the smallest that hole can ever be is 0.993. The largest that shaft can ever be is 1.002. So we're going to have an interference there, negative 0.009. The negative means an interference. Let's look at those two parts in their other conditions. So let's move that hole up to the largest the hole can be. So the largest the hole can be is 0.997, and the smallest we can make that shaft is 0.998. So it's still going to be an interference. The hole is always smaller than the shaft, so there's always interference. And in this case, our interference ranges from 0.001 to 0.009. And our third type of fit is a transition fit. So a transition fit can vary. It could have either a small clearance or a small interference between the mating parts, depending on the actual sizes of the shaft and hole. As it normally produces either a slight clearance or a slight interference, little force, if any, is required. So let's take a look at these two parts again. So the smallest that hole can ever be is 0.997. The largest that shaft can ever be is 1.005. At that condition, there's going to be an interference of 0.008. But if we made the hole as big as it could be, 1.003, and the shaft diameter as small as it could be, 0.995, then we're going to have a clearance fit of 0.008. So when the shaft is as large as it can be and the hole is as small as it can be, there's an interference. When the shaft is as small as it can be and the hole is as large as it can be, then you'll have a clearance. Okay, so in your ILM booklet, I'm going to get you to do the questions for objective number 1. So question 1 is some terminology. So once you've completed those, go ahead, pause the video, complete those, and we'll take a look at the answers at the end of this video, or you can check them in the back of your book. So objective 2, interpret limits and fits on prints. Now that you're familiar with the terminology and purpose of limits and fits, you need to practice using them. This objective allows you to practice calculating limits of size and tolerance. So objective 2 is no new information, but the exercise gives you this figure, figure number 7, with a nominal shaft diameter and a nominal hole diameter, and a table underneath it. So what it wants you to do, in this case, let's start out with let's start out with line number 1. You're only going to fill in the empty cells, not the shaded ones. So whole upper limit size. So they want to know the upper limit of this. So 2.372 plus 0.006. So 2.378. And then they also want to know the whole lower limit of size. So 2.372 minus 0.006 would be 2.366, I think. Let's take a quick peek. Yeah, okay. So if we were calculating that one, we would have 2.378 as our upper limit, 2.366 is our lower limit. So our tolerance, because we're going to subtract those, remember, we're going to get 0.012. So you're going to do the same thing with the rest of these. 1, 2, 3, 4, 5, 6 of them. The next 2 are inches, the next 3 are inches, and the last 3 are millimeters. So just fill in the blank cells in your table. Okay, so pause them, go ahead and do that. And we're going to take a look at Objective 3. Objective 3. When you've completed this objective, you'll be able to calculate allowances on mating parts. As you saw in Objective 1, an allowance is the intentional difference in size of mating parts at their maximum material condition. You calculate the allowance by subtracting the largest allowable shaft from the smallest allowable hole. A negative value equals interference, while a positive value equals clearance. In transition fit, either clearance or interference is possible, depending on the size of a particular shaft hole parent. You cannot calculate the allowances unless you know the MMC of both mating parts. In this objective, you calculate the allowances of several combinations. So objective number 3, they've given us, instead of just giving us a basic dimension, they've given us the limits of size. So maximum material condition and least material condition for the shaft, maximum material condition for the hole, and least material condition for the hole. So on the hole, the maximum material condition is when it has the most material still there. So the diameter would be smaller, 1.000. The least material condition is when as much material has been taken away as possible. So the diameter would be 1.002. Okay, so what we're going to do in this one is you're going to calculate the allowance and then figure out what type of a fit it is. So let's take a look at the table. We'll just walk through the first one together. Okay, so objective 3. So in this case, we want to subtract the largest shaft diameter from the smallest hole diameter. So that would be, let me open up my little calculator here if it will let us. Okay, I can't get my calculator to pop up here, but that's okay. So the largest shaft is going to be 0.999. The smallest hole is going to be 1.000. So the smallest hole minus the largest shaft is 0.001. And since it's positive value, we get a clearance. Let's try one more. Let's look at the next one. So we're going to take the smallest size hole, so 1.266, and we're going to subtract the largest diameter shaft from that, 1.278. So if you use your calculator, 1.266 subtract 1.278, you're going to get a negative 0.012. So in this case, we have an interference of 0.012 inches. So go ahead and complete the next 4 exercises in that table. Pause your answers and come back here to check your answers. Okay, so we had our answers for objective number 1, our answers for objective number 2, and our answers for objective number 3. And at the back of your ILM booklet, there's also a self-test. So questions 1 through 9, and your answers are given in your ILM booklet for those as well. That concludes our review of ILM 150104G, Limits and Fits, Objectives 1, 2, and 3.